In the last video, I made this bold claim that the Laplacian was applicable almost everywhere, but I didn't actually show you any applications. So in this video, I'm going to derive the Laplacian. I'm going to sort of reinvent it just by basically applying Ohm's law and in the context of an electrical circuit. So I'm going to take an electrical circuit, which is going to be represented like a graph, and the wires will be edges. And we're going to look at the basic things you might study or ask questions about on that network, apply Ohm's law, try to come up with some elementary questions that we might want to solve computationally, and discover that the Laplacian falls out in the most natural way. So if you like, you can think of this as the main equation for today. And this, I know I'm not using the standard variables here, but this is a potential. This is an electrical potential on the vertices, and then this is going to be the net current. All right, that's the amount of current entering or leaving the system at each vertex. So this is a system of linear equations describing what's happening in an electrical circuit. So just as a reminder, Ohm's law, if I look at just one edge in this graph, that is to say two nodes, I guess you might call them, terminals in a electrical circuit, and I've got one wire between them. When I look at this wire, I could talk about the voltage on this wire, V. I could talk about its current. I'm going to use W here. I know that people like to usually use I for current, but I use I for pretty much every index, and treating it like a vector now would just be too weird for me. And there's some resistance. Now, put resistance below the line. There's a little asterisk here, which is to remember that the resistance doesn't care about the direction, right? So whereas the voltage is an electric potential difference, it's a change in potential depending on the direction, and the current also has a direction. So even though the graph is not directed, we will at least orient it so that we can say whether positive or minus of these values corresponds to going in the direction of the orientation or against the orientation. And the little asterisk here again is that the resistance is independent of the orientation. And that fact that the resistance is somehow slightly different in this setup will also come out in the equations. All right. So what is Ohm's law then? It says that the current times the resistance is equal to the voltage. So I can just write V equals RW here. And this is just a statement about what's happening on the wire, that is on the edge. If instead I want to know what's happening at the vertices, well, there are things going on there as well. We can think about there being a potential at the vertices. Again, this is at the vertices. Or the net current. And I'm going to give these names as well. Let's call this P, and let's just call this C. Now, the potential determines the voltage, right? The potential difference, well, that is the voltage. So in fact, V is just equal to whatever this potential is at B minus the potential at A. All right. And now, so here's a larger circuit, and of course there could be some say net current coming in, some net current coming out, and within the rest of this circuit, at every edge we have this identity. And so the idea that we're going to try to push on here is to express Ohm's law everywhere, that is on every edge. And part of what we're doing here is a basic, I would say, power tool for anyone doing anything computational these days, which is to be able to express a large number of things in a simple vectorial form. So certainly anyone who's ever tried to program in MATLAB, sorry for your situation, knows that things go much better, much easier to express, faster to compute if you can just express the thing you want to compute directly as vectors. So here it looks like I have a collection of identities for one for every edge. And if I can just write it all as one simple vectorial linear system of some kind, then everything is going to be easier. Of course, the same is true not just in MATLAB, but let's say NumPy or whatever your favorite numerical linear algebra package is. All right, so if we have a current, that's going to be a vector in Rm, right? For every edge, right, there are m edges. For every edge, I'm going to get a current on that edge. And similarly, a potential, you could think of that as a real number associated with every vertex. So that's going to be a vector in Rn. And we have linear transformations from Rm to Rn determined by the graph, right? That is the boundary matrix and its transpose. The transpose is also called the co-boundary matrix. But if I apply this boundary matrix on the current, what I'll get is the net current. Okay, so that's gives me something on the edges, gives me something on the vertices. And similarly, if I take a potential and I take its co-boundary, that gives me the voltage. You can work this out pretty easily. You can see that this co-boundary matrix, when I apply it to a particular potential, it's just going to give, for each edge, it's going to give me plus one side minus the other side for the plus one and the minus one that are in each row of this matrix. Okay, so what now? Well, this gives us 4 of the 5 objects that we cared about. Remember, we had voltage, current, and resistance on the edges. We had potential and net current on the vertices. For now, just for now, we're going to assume something that's going to make things much simpler for us, which is we're going to assume that all the resistances are the same. So we'll pick some unit, and so the resistance on every edge is just 1. We'll get rid of this assumption in a bit, but it's gonna help a lot. So Ohm's law in this case is going to be just instead of voltage equal to the resistance times the current, it'll just be the voltage is equal to the current. All right. So using these transformations, we can rewrite Ohm's law. So Ohm's law was about the voltage now, and this is going to be the voltage on all the edges, right? So this is a vector in Rm for every edge. It gives me the potential difference or the voltage, and that's going to be equal to this other vector in Rm, which is the current. Okay, these are both in Rm. And again, this is voltage and current. Now, here's a natural question you might ask. If I know what the desired net current is, or if maybe I know what the measured net current is, that is, I know where and how much current is entering or leaving the circuit, I might want to find the potential at all the vertices. So plugging in directly these identities from the previous page, we know that the net current is just equal to the boundary times the current. Let's call this dW, which by Ohm's law, if I plug in Ohm's law here, this is just the boundary times co-boundary of some potential. That's the potential that we wanted to find, and this is the Laplacian. So the Laplacian of the graph associated with that circuit is this. And so this tells us exactly how to do the computation. In fact, it's all here. We just need to solve this linear system, which is LP equals C, which is the system that I started with on that first page. But there's a problem. You see, if I ask you to solve a linear system, one thing that's kind of useful is if that linear system is non-singular. That is, there actually, is an inverse, and I can just always solve it. But the Laplacian is not. I shouldn't say it's not non-singular. It is singular, right? There, in fact, are vectors, non-trivial vectors in the kernel of this matrix. However you want to think about singularity, the determinant is 0. There are values of C for which there is no potential to realize that current. And so that seems maybe disheartening, but there's good news, because we actually know exactly when we can solve this system. So let's see. We want to solve LP equals C. When can we do it? Let's use this notation here. This bold, it's a bold 1. It's the all ones vector in Rn. And so one thing you might have observed or guessed is that if I take Lx, right, so after I apply L to some matrix, and if I multiply it by the all ones vector, I could write this out. Multiplying by the all ones is the same as adding up all the elements. So I can sum over all the elements, and then the elements of Lx are just, each one is the sum over all j, such that ij is an edge of the difference. Right? These are the differences along the edges. But if you look at this sum, it's going to sum over all ij, but it's going to hit every edge exactly twice. Once from the perspective of I and once from the perspective of j. That is, we're going to add it from both sides. And so I could write this as the sum over all ij in the edges of xi minus xj plus the xj minus xi. But it's not too hard to see that this just cancels out, and this is just 0. All right, so the vectors that we get out of Lx, that is everything in the image of L, is going to have the sum of its coordinates will be 0. Or, in other words, everything in the image of L will be orthogonal to the all ones vector. But in fact, this is the only constraint that we would put on the image of L, as long as G is connected, right? So if G is connected, this is the only linear constraint that you need on the image of L. And so if you have any net current where the net current, if it sums to 0, then this linear system has a solution. All right, so that's good. So we can at least know very quickly whether or not we should be able to solve it or not. You may also recall from linear algebra that if you have a system like this that doesn't always have a solution, when you do have a solution, you usually have an infinite number of them. And so in this case, we actually will expect to see not just one solution, but some, in this case, just one-dimensional space of solutions. And that space is pretty easy to describe as well. All right, but let's find a specific case. So I think the easiest case and the most natural one, and the one that we're actually going to use to solve the original problem I proposed, is the case where you're going to inject 1 unit of current at S, and so here comes 1 unit of current at S, and you're going to extract 1 from T. So it's like 1 minus 1 is the net current, and everything else is 0. I could put some zeros in here. Now this vector, this net current, if I add it up, I get 0. So it is the case that C transpose all ones is equal to 0. It's orthogonal to all ones. And so I expect to find a solution. So I would find LP equals C. There is a general way of finding such solutions when you know you have them. In fact, there's a kind of inverse, it's called the pseudo-inverse. We won't talk too much about it here. But if I took this pseudo-inverse times C, that will in fact give me P. And what this pseudo-inverse does is it gives you an inverse in the projection space, in the space of really of the image of L. Now, you might recall, if you ever studied these circuits, that there is something called Kirchhoff's potential law. 2 H's, 2 F's. Kirchhoff's potential law says that the flow in should equal the flow out. So, except for these cases where current is entering or leaving the system, everywhere else, the total flow in should be equal to the flow out. This is the same, I'll give it a different, I'll just put a bar over it, is saying that the net current is 0. Look at what happens to potentials as other choices of P. If I were to add in some multiple of the all ones vector, that is, I change the potentials everywhere. This is a case where I would expect also to keep all of the voltages the same, because I've added the same amount to every potential, so all the differences should all stay the same, so all the currents should stay the same. This, if I just multiply it out, or I distribute this over the addition, this is just L times the all ones, which this part is 0, so this is just, again, LP. So this is how I might go from one solution, P, to other solutions. In fact, this will give me the entire space of solutions. Now, how do you do a little more? Let's try the following. Say I have a network like this, and I want to compute the effective resistance between two vertices. So I still have my individual edges are all resistors of the same unit size. But now if I look at two other vertices in the network, I would like to know what the effective resistance is. That is, the whole network now is acting as a resistor, and I want to know what would that resistance be between some vertex S and some other vertex T. And the way to do this is to just first, again, take a unit of current in at S and out at T, solve for the potential, and now from Ohm's law again, the potential difference divided by the current. Well, we know what this is. This is the difference in potential. And then we know how much current is flowing. Now, it's just 1. It's going to be equal to that effective resistance. So that's, again, just PS minus PT. So when I solve for the potential, I can also get the effective resistance just by looking at the difference in potential. Now, what about this case, this really important case when the edges actually have different resistances? Part of the reasons we start with the unit resistance case is that it naturally gives us our standard Laplacian. And in the case of other resistances, we're going to get a slightly different Laplacian. It's going to have some weights. And instead of representing the resistances as a vector in Rm, instead I'm going to treat it as an m by m matrix. This kind of goes along with the fact that the resistances had this, let's call it an indifference to the direction or the orientation of the graph. And now, if you wanted to write out Ohm's law, here we would have that the voltage is equal to not just the current, but the current scaled by W. Oh, I guess I already wrote it right here. So this is m by m matrix by m by 1, so this whole thing is m by 1. This is the currents, all the currents times the resistances for each edge. And so what we'll do is we'll define this new kind of Laplacian. I put a little squiggle on top, and then this weighted Laplacian has the following form. It's going to be boundary times the inverse of R. This is a diagonal matrix as well. It just has 1 over Ri for each diagonal entry. And then again times the co-boundary matrix. So you can see at least that if I had all unit resistances, this would be the identity matrix. The inverse would also be the identity matrix, and that would be our standard Laplacian. So this is a generalization of what we've done before. And now if I'm given some net current, I know that that net current is the boundary of a current, which is equal to, by Ohm's law, if I rearrange this one's true if and only if I take R inverse coboundary of P is equal to that current. So the boundary of the current will be the boundary times R inverse coboundary of P, which is just our new Laplacian system. So again, we'll solve LP equals C, and that will be the system that describes how to get a potential from a net current given these new resistances on the edges. All right, well, that's it.